Hey everyone, Mr. Fransky here. So in the last video we talked about the theory of the fundamental theorem of calculus for the first part. And in this video we're going to talk about some examples where we can actually apply this. AP always asks a question about fundamental theorem of calculus part 1. They give you a graph and they ask you some questions about it. So today we're going to solve some integral and graph problems using the first part of fundamental theorem of calculus. So vocab we're going to see, we'll see that accumulation function again for sure. The tower of functions is really important in solving the graphical type problems. And also we'll talk about dumping in an x. So that's where you have an integral, you have the x on the top, and you're just dumping it into a dummy variable for a function. So let's take a look. So what would a problem look like? Well, I got to be honest, some of them are pretty easy. If we want the derivative of the accumulation function from 3 to x of sine of t dt, this means that you would be integrating or finding the area under sine from 3 to a value. That's pretty hard to do. But the derivative, if you have sine, the derivative of that accumulation function, 3 I guess, so pi is like around here somewhere, so 3 would be like here. The derivative of this is just the height of the function. So you take that x, dump it in. It is sine of x. It is that easy, folks. That's it. Next one, if you want to try it yourself, pause the video for a second, see where that x goes, give it a shot. Alright, let's see what happens. All you do is dump the x everywhere you see a t. That's it. So it is e to the negative 3x times x squared. That is your derivative. It's that easy. People always ask me on this, wait, don't you have to chain? So my answer is you always have to remember how chaining works, but you're taking the derivative with respect to x, not with respect to t. We are not deriving this function. We're deriving the accumulation function, so the x just gets dumped in. That's like saying, nope, I don't want to do that. I'm not going to try to make it more complicated than it has to be. So here's something a little bit different. This time we have an x squared. So this is where we're going to have to chain. We're going to dump the x squared in, and then we're going to chain on x squared. So this is going to be natural log of x squared. Just leave that part alone. Then you multiply by 2x. So you take the derivative of the function by itself, and then you chain on the x squared. The reason for this, the way I think about this, is let's say that f of x is the integral from 3 to x of ln t dt. So notice it's just an x up here. So let's say that h of x is equal to f of x squared. Okay, so this is a composition of functions. This is something you focused a lot on in pre-calc and in advanced algebra. So if f of x is integral from 3 to x of ln t dt, then f of x squared would be the integral from 3 to x squared ln t dt. That's just a substitution. X squared, x squared. So then if we want h prime, we have to do chain rule because this is a composition of functions. So that means we have to do f prime at x squared. So you leave the x squared alone, but you do the derivative. That's this part. You just take the derivative, leave the x squared alone, and then to chain, we have to multiply by 2x, which is this part right here. So if you have something up top, you just dump it in, and then you multiply by the derivative. Let's try another one like that. So this time we have a much more complicated function. But once again, if you want to pause the video and try this, give it a shot. It's not too bad. All right, let's see how it went. So we're going to take this, we're going to dump it in for t right there. And then we're going to multiply by the derivative of the baby function, which is this whole mess with the x. So the derivative of this will be, I need some parentheses here, I think, tan inverse of x minus ln x plus x all to the 4th power plus 1. Now we're going to multiply by the derivative of the baby. This whole thing is the baby. So the derivative of the baby is 1 over 1 plus x squared. That's the derivative of tangent inverse. Minus 1 over x, that's derivative of natural log. And then plus 1, that's derivative of x. And this is your derivative of the accumulation function because we have to multiply by the derivative of the baby. Crazy. So, I want you guys to try this one. So, once again, pause the video, give it a shot, and see how it goes. So we're looking for the second derivative this time. Alright, let's see how you did. So, first thing we need is f prime of x. Well, that's the derivative of the accumulation function, so we just dump the x right in there. So that is going to be tangent of x. The second derivative of x then, well, we just take the derivative of tangent, which is secant squared x. And that's your answer. Second derivative of the accumulation function. First one's just tan because you just dump it in. The second one gives you secant squared. So this last one that I have here is a little bit more complicated because we have an x in the bottom and on the top. I want to see if we had one like that before. I think I might have made a mistake, or I might have missed one. No, I didn't. Okay. So a function like this, we have an x on the bottom and the top. Fundamental theorem is only good if you have an x on the top. So the bottom here is going to throw us off a little bit. And before I actually do this one, I want to try one more. I thought I had it in here as an example, but I can't find it. So let's say we wanted to find the derivative of the integral from x to 5 of, I don't know, maybe cosine t dt. So the issue here is, once again, our fundamental theorem is only defined if we have x on the top. So what we're going to do is we're going to use our properties of integrals to get the x on the top. So this would be the derivative, d dx, of negative integral 5 to x cosine t dt. So to get that x on the top, you make this negative because that'll flip the limits. So then it's just going to be negative cosine x. That's it. Because we just dump the x in now, and then that negative sticks around. Because you can pull it out, because it's a derivative, so you can pull the negative out, and then you do the derivative, dump in the x, and the negative still sticks around. So that's going to be important for this one. So the way I think about this is, you've got your function, t to the fourth, so t to the fourth is like kind of a parabola looking thing, and x will be like here, and x squared will be somewhere over here. So many ways to think about this, but I want the area between x and x squared. To get that, I want to introduce a constant somehow. So we could think about this as, if we have integral 0 to x, let's use some different colors here. So the red, we do integral 0 to x, and the green, we'll do integral 0 to x squared. To get the purple area, the area that I want between x and x squared, I can do the green minus the red. The green minus the red. So I'm going to do integral. So I want the derivative of the integral from 0 to x squared of t to the fourth dt minus my red integral. Integral from 0 to x of t to the fourth dt. So this will always work. You can always take the top value, integrate from whatever value you want. I could have started at 1 if I wanted to. I could have done something between them even, but that would be maybe more difficult. So now my derivatives, I just dump in. I'll go back to purple here. So this is going to be x squared to the fourth. On this one we have to chain. So we multiply by 2x. Then we subtract off x to the fourth. Make that look a little prettier. That's x to the eighth times 2x minus x to the fourth, which is 2x to the ninth minus x to the fourth. Now, there are lots of other ways to do this problem. One way that I like to do this is if you say, hey, let's introduce like some c value in here. Okay? It doesn't matter what it is. You can make it like, I don't know, 20. Let's say. So you could integrate from x to 20, and we have the derivative of this, from x to 20, t to the fourth dt, and then we add to it the integral from 20 to x squared, t to the fourth dt. So now we have to use what we talked about up here, where you have the limit on the bottom. We don't want it on the bottom, we want it on the top. So this is d dx, negative integral 20 to x, t to the fourth dt, plus integral 20 to x squared, t to the fourth dt. And you can see now, because the value of the constant doesn't matter, we have exactly the same thing we had up here. We just use 0 instead of 20. So now we have 20 to x squared minus 20 to x. That's exactly what we have up here. You'll end up with exactly the same algebra at this point. So a few different ways to do a problem where you have an x in the bottom and the top. So one more type of question they might ask you with this first part of the fundamental theorem. They might say, hey, what is a function that has this derivative? So they might give you anything. In this case, we have 3x squared minus or times sine x. So if we want this to be the derivative, we can kind of cheat now because this is difficult. It's a product. I can't really think of something off the top of my head that has that as the derivative because product rule doesn't work very well like that. But what we can say is, hey, let's define capital F of x as the integral from, pick your favorite number, let's say 5, I've been using 5 a lot, to x of 3t squared sine of t dt. Because what is f prime then? F prime of x, you just dump the x in. It's 3x squared sine of x, which is exactly what they told me they wanted the derivative to be. So it kind of feels like cheating, but this is a totally legit way to define a function. And then the derivative, you just take the x, dump it in, and you are all done. So now we're going to add one more little piece to it. Say, okay, this is the derivative, but I also want 4,0 to be on the function. I want 4,0 to be on the function. Well, on the last problem, if I plugged in 4, f of 4, that would be the integral from 5 to 4 of this function, which would be pretty difficult to do. I have no idea how to find that area. Okay, I don't know how to do this. But if I know that when I plug in 4, I want it to give me 0, that I can deal with. Because there's one thing I know. So let's leave the bottom blank for a second. We're going to go up to x, 3t squared sine of t dt. Whatever the bottom value is, when I plug in 4 up here, I need it to give me 0. Well, there's one thing we know about integral properties. If I integrate from 4 to 4, that's going to give me 0 for any integral that you have. So now we have that f of 4 will be the integral from 4 to 4. Doesn't matter what this function is. 3t squared sine of t dt is fine. That's going to give me 0. So I've satisfied the only condition that they gave me. When I plug in 4, I get out 0. One more. What if I want 4, 2 on the function? Well, messing with that bottom limit is not very useful. So I'll put in my function here again. If I change this bottom limit to anything else, if I try to make this integral be 2 when I plug in 4, like maybe I say, well, maybe if this is like 3.6 and I plug in 4 at the top, maybe I'll get out 2. That is not going to work because you'd be messing with this value all day trying to get it to be 2. But watch this, and this is where it really feels like you're cheating. I'm going to leave this as a 4. Now when I integrate from 4 to 4, it'll give me 0. All I have to do to get that 2 to happen, add 2 on the outside. I know it seems cheap, but that's all it is. Now if you take the derivative of this, this is a constant, so it disappears. When you take the derivative, you'll just dump the x in. So f prime will still be 3x squared sine x. So that's true. And when you plug in 4, 4 to 4 gives you nothing, and you add 2, so 4, 2 is on that graph. Crazy. I have some problems like that for you here that are just like we had in 5.4a that use the first part of the fundamental theorem of calculus. So if you want to pause the video here, do a little bit of bell work, and give these a shot, you can, and then I'll go through them with you. All right, let's take a look at these and see how you did. So the first one, pretty straightforward. We have an accumulation function, just integral from 3 to x of sine of t dt, and we want to find f prime of x. That is the derivative of the accumulation function. So we just take that x and dump it right in there. So that is sine of x. That's it. The next one, we're looking for dg dx. So g of x is the integral from e to x. Again, e is just a constant. T squared ln t dt. So we just take the x and we dump it in everywhere we see a t. That's it. X squared ln of x. That's it. Next one, this one's a little bit different. So we have the integral from x to 0. We don't like the x on the bottom for fundamental theorem of calculus because it has to be where the function ends. So what I'm going to do is I'm going to flip it around. So we have d dx negative integral 0 to x e to the t dt, which is going to be negative e to the x. Because you can pull that negative out to the front of the derivative, then take the derivative, which is e to the x, and the negative applies afterwards. The next one we're going to have to use chain rule on, because we have the integral from 3 to 2x. So I'm going to take 2x, I'm going to dump it in where that t is. So I have 2x to the 3 halves power. Then we multiply by the derivative of 2x, which is 2. That's our chain rule. Remember, you only chain on the x part, never on the t part. You just dump it in for that part. So the next one, this one has x's on the bottom and the top. So a couple ways we can think about doing this. One way is to say, well, I want to really just subtract everything before the bottom value, because if you think about this function, I have no idea what this function looks like. You could probably figure it out, but let's say it looks something like this. So if this is my root x, and this is my x to the 4th, I want the area in between. So what I can do is say, okay, I'm going to take the entire area from 0 up to x to the 4th, then I'm going to subtract off the root x. Okay, so I'm going to do the derivative of the integral from 0 to x to the 4th, 1 over root 1 minus t squared dt. Then I'm going to subtract off the integral from 0 to root x. So I'm taking away the white area here of 1 over square root of 1 minus t squared dt. So we take the derivative of each part separately. So the derivative of this guy is going to be 1 over the square root of 1 minus x to the 4th squared times 4x cubed, because we have to chain on that x to the 4th. And then it'll be minus 1 over the square root of 1 minus root x squared is just x, multiplied by the derivative of the baby function here, which would be 1/2 x to the negative 1/2. So you can clean this up a little bit more. I mean, this is 1 over 2 root x. And then here, x to the 4th squared, that would be x to the 8th, but I'm out of space, so I'm just going to leave it like that. And because you don't have to do algebra, that is absolutely acceptable for an answer. If it was a multiple choice, they'd probably have some choices that had some better algebra done on that one, though. Cool. Okay, so the first part of Fundamental Theorem of Calculus gives all kinds of fun AP problems. They give you lots of graphs like this where it's easy to find areas. They might give you some semicircles, some lines, I'll make triangles, maybe some trapezoids, and then they'll define a function. And the first thing they'll ask you is usually just to find some points. So let's say that g of x is the integral from 1 to x. So we're starting at 1, and we're going to go to x of this function. So let's say this function right here is lowercase f of x. Okay, and often what they'll actually do is they'll just put f there, because then they don't have to worry about any confusion with the t's and the x's and whatnot. So let's find some values. G of 2. So g of 2, we did this kind of in the first video, integral from 1 to 2, little f of t dt. So 1 to 2, that is this area right here. Well, that area isn't too bad. It's a quarter of a circle with radius 1. So it's 1/4 pi r squared. The radius is 1. So that is pi over 4. Nifty. G prime of 2. So the whole point of Fundamental Theorem of Calculus is that we are looking at the derivative of g. This graph right here, f, is the derivative of g. So what helps me to do this is I make what I call the tower of functions. Every time that you have a function like this that's defined in terms of an integral, I think the tower of functions is just incredibly helpful to make. So what I do is I would start at the bottom. So I say g of x itself is the integral from 1 to x, f of t dt. That was given to us. G prime of x is the graph that we're looking at. So it's f of x. And sometimes I'll put next to that, it's the graph. And then if I wanted g double prime of x would be f prime of x, because we're just adding primes at this point. So that would be the slope of the graph that I'm looking at. So let's see here. So g prime of 2. G prime of 2, if I look at my tower of functions here, g prime of 2 is going to be the graph value when x is 2. Well, when x is 2, the graph value is 0. So don't get yourself too hung up on this, because a lot of people say, oh, it's not differentiable at 2, because this function, f, is not differentiable at 2 because it's a corner, but g is just, the derivative of g is just the graph value at that point. That's all there is to it. G prime of 3, oh sorry, g prime of 2, this was not x. G prime of 3, again, let's check our tower. If we look at our tower of functions, g prime is just the graph value when x is 3. Looks like that value is -1. Again, some people say, wait, but it's not differentiable there. F is not differentiable there, but g prime is just the graph value, which is -1. It's true the second derivative would not be defined there because this graph would not have a slope, but first derivative of g, just fine. It's -1. G double prime of 4. Uh-oh. I don't know why I chose that value. Looks like 4 actually is at the end of my interval, so that wouldn't be a value. I'm wondering if I didn't make this graph just a little bit wrong. Let's see here. Yep, that was supposed to go up a little bit further. I'm sorry about that. So this was actually supposed to go all the way to 5. I apologize. So g double prime of 4 then is going to be the slope of this graph at 4. Looks like rise over run there is +1. So if I had made my graph correctly, that would have worked out just fine. So they almost always start with something like this. What is g prime of this value? What is g double prime of this value? And then we get into some more exciting stuff. So let's take a look. What is the equation for the tangent line to g at x equals 3? Here's our g of x function. It hasn't changed. It's the accumulation function from 1 to x. So what we need to find the tangent line, it doesn't change. The rules don't change. We have a point and a slope. Point and a slope. So I'm going to write out my tower of functions again. Integral 1 to x, f of t dt. That's our g of x. G prime of x is equal to this graph that I'm looking at, f of x. So it's the graph itself. The accumulation function, I guess would be worth writing here, is the area. Should have put that on my last one too. So this is the area. The derivative is the graph itself. And then g double prime is going to be f prime of x, which is the slope. Okay, so the slope here actually we already found in the last one. That's going to be g prime of 3. G prime of 3 is the same as f of 3. F of 3, -1. So we've got our slope. The point, well, x is 3. To find the y value, that's going to be g of 3. G of 3 here, I'll do that up here, would be the integral from 1 to 3 f of t dt. Because that's just the g function. So we're looking for area there. We already found this area. It was pi over 4. And then this guy right here, so if we continue to integrate to the right, it looks like the area right here is half of a unit square. So this is going to be 1/2. And because it's below the graph and we're going in the positive direction, it's negative. So the point is pi over 4, area above, minus 1/2, the area below. So pi over 4 minus 1/2. That's the y coordinate. So then, put this into point slope form. Y minus pi over 4 minus 1/2 equal to the slope, -1, times x minus 3. And that's your tangent line. And again, it's weird because we never see the graph of g. Graphing g is difficult. You'd have to think about kind of if you're accumulating positive area or negative area. It's not easy to do. But as long as you have the tools on the derivative right here to be able to find the function values and also the derivative, you're good. Now we ask where g has a maximum or a minimum. Well, a maximum is going to happen when the first derivative changes from positive to negative. So we're looking for g prime to change positive to negative. Well, g prime is f. So I'm looking at the derivative. I want to change it from positive, which would be above the graph, to negative, which is below the graph. So there's a max at x equals 2. Why? Because we change from positive to negative. Graph values here. F values, or the derivative of g, changes positive to negative there. So max at x equals 2 because g prime, which is f of x, changes positive to negative. And then again, if I had drawn my graph correctly, we would have a minimum at 4 because we changed negative to positive. So minimum at x equals 4 because g prime of x, which is f of x, changes negative to positive. That's it. We're looking at the derivative. So don't let this fact that we're doing accumulation functions get you down. The only thing you have to worry about is how does the derivative change. You can also then tell when it's increasing, decreasing, right? G is increasing whenever f is positive, so all the way up to 2. and it's decreasing up to 4. Kind of cool. They always love to ask about inflection points. So, tower of functions again. And it seems like overkill, but you need to be able to do this. 1 to x f of t dt. G prime of x is f of x. That's the graph we're looking at. And g double prime of x would be the slope. So that's going to be important, or f prime of x. That's going to be important for this one because an inflection point happens when there's a change in g double prime of x. Well, g double prime of x is f prime of x. So I'm looking for a change in slope. So let's mark the slopes here. At this point we have negative slope, then we change to positive slope, then we go back to negative, then we have continued negative slope here, and then we change positive at the end. So it looks like we have inflection points at x equals 0, x equals 1, and x equals 3. Because those are the two spots that g double prime of x, which is f prime of x, changes sign. Cool. That's it. A lot of AP problems that look like this. Every single time there's an AP test, they have some kind of a problem like this with an accumulation function, guaranteed. All right, so now that we've learned how to use Fundamental Theorem of Calculus Part 1, we're going to check out Part 2 in the next video, which is probably going to be more useful in a lot of the kind of more applied integrals we're going to do later on in the book. And so make sure you check it out and you learn how to use antiderivatives to solve integral functions. It's pretty cool. I'll see you there.